Hi everyone, welcome to Conformal Mapping under the topic Complex Differentiation. The contents we are going to discuss are Conformal Mapping or Transformation, Isogonal Mapping, Critical Points, Standard Transformations. Conformal Mapping. Consider the complex variables z equal to x plus iy and w equal to u plus ib. Then both z and w can be represented on two separate complex planes. One is called z plane and another one is called w plane. If the point z moves along some curve in z plane, then the point w will also move along a corresponding curve in the w plane. Since to each point x, y of z plane, there exists a point u, v in w plane. If we describe a closed curve R in Z plane, we shall get in general a closed curve R dashed in W plane. We say that a curve C in Z plane is mapped onto the corresponding curve C dashed in the W plane by the function W equal to f of Z. Therefore, W equal to f of Z is said to be a transformation or mapping. Conformal mapping. Suppose a point P in Z plane corresponds to a point P dashed in W plane by the transformation W equal to f of Z. If any two curves passing through the point P map into two curves through P dash such that the angle of intersection at P is equal to the angle of intersection of the corresponding curves at P dash, both in magnitude and direction. Then the transformation W equal to f of Z is called a conformal mapping or transformation. Therefore, a mapping or transformation which preserves angles in magnitude and in direction between every pair of curves through a point is said to be conformal at that point, which is shown in this figure. Isogonal transformation. The transformation which preserves angles only in magnitude but not in direction between every pair of curves through a point is said to be isogonal at that point. For example, the transformation W equal to Z bar is isogonal transformation. Next, critical point. A point at which f dash of Z equal to 0 is called a critical point of the transformation W equal to f of Z. That is, at the critical point, the transformation W equal to f of Z is not conformal. Now let us find the critical points for the transformation W square equal to Z minus alpha into Z minus beta. We know that critical points occur at dw by dz equal to 0 and dz by dw equal to 0. Therefore, differentiating the given function with respect to z and w, we get the points z equal to alpha and z equal to beta and z equal to half into alpha plus beta, which are called the critical points of the transformation. Now let us discuss some standard transformations. First one, translation. The transformation W equal to Z plus A, where A is a complex constant, represents a translation. Let Z equal to X plus Iy, W equal to U plus Ib, and the complex constant A equal to A1 plus Ia2. Then U plus Ib equal to X plus Iy plus A1 plus Ia2, substituting in the transformation W equal to Z plus A. So the real part u equal to x plus a1 and imaginary part b equal to y plus a2. The image of the point xy in z plane is the point x plus a comma y plus b in w plane. Therefore, the transformation w equal to z plus a translates every point xy of z plane through a constant vector representing a. Every point in any region of Z plane is mapped upon the W plane in the same manner. If the whole W plane is superposed on Z plane, the figure is shifted through a distance given by the vector A. Therefore, in particular, this transformation maps circles into circles. Also, the corresponding region in Z plane and W plane will have the same shape, size, and orientation. Second transformation, magnification. The transformation W equal to AZ, where A is a real constant, represents magnification. Let W equal to AZ, which implies U plus IV equal to A into X plus IY. Therefore, the real part U equal to AX and the imaginary part V equal to AY. It is clear that the image of any figure in Z plane is magnified A times without any change in its shape and orientation. This transformation maps circles into circles. Here the images are magnified A times in W plane. Third transformation, magnification and rotation. If we consider A as a complex constant, then it represents both magnification and rotation. Let Z equal to R e power I theta. Then by the transformation W equal to AZ, we get the real part R equal to R alpha and phi equal to beta plus theta. The image theta of any point in Z plane is obtained from P by rotating OP through an angle alpha equal to argument A and magnifying OP in the radius modulus A, which is shown in this figure. Thus, the transformation W equal to AZ corresponds a rotation together with the magnification. Now let us discuss few problems. Find the mapping of the circle modulus Z equal to 1 by the transformation W equal to Z plus 5 plus 2i. So this W equal to Z plus 5 plus 2i, we know it is a translation. It translates the circles into circles in W plane. Let us find out now. Now we know that Z equal to X plus Iy and W equal to U plus I. Substituting, we get U equal to X plus 5 and V equal to Y plus 2. So expressing X and Y in terms of U and V, we get X is equal to U minus 5, Y is equal to V minus 2. Now we are given the circle modulus Z equal to 1. We know that mod Z equal to 1 is a circle with center at origin and radius 1 unit. Now we have to find the image of this circle in W plane. Mod Z equal to 1 can be rewritten as x square plus y square equal to 1 in Cartesian form. Now substituting for x and y, we get u minus 5 whole square plus v minus 2 whole square equal to 1, which is also a circle with the center at 5, 2 and radius 1. So the image of the circle mod Z equal to 1, that is x square plus y square equal to 1, is another circle u minus 5 whole square plus v minus 2 whole square equal to 1 in W plane. Therefore, the transformation W equal to Z plus 5 plus 2i maps circles into circles in W plane. Next one. Let us find the image of the circle mod Z equal to C by the transformation W equal to 5Z. This is under magnification. Now W equal to 5Z, equating real and imaginary parts, we get U equal to 5x, V equal to 5y. Expressing x and y in terms of U and V, we get x equal to U by 5, y equal to V by 5. Now the circle mod Z equal to C, writing in Cartesian form, we get x square plus y square equal to C square. Now substituting for x and y, we get u square plus v square equal to 25c square, which means that the image of the circle mod Z equal to C is another circle u square plus v square equal to 25c square in W plane. Here the image is magnified 5 times in W plane under the transformation W equal to 5z. Now let us find the image of the circle mod Z equal to K under the transformation W equal to 1 minus I into Z, where 1 minus I is a complex constant. Here the image will be with the magnification together with rotation. Now W equal to 1 minus I into Z. Equating real and imaginary parts, we get U equal to x plus y, V equal to y minus x. Expressing x and y in terms of u and v, we get x equal to u minus v by 2, y equal to u plus v by 2. Given the circle mod Z equal to k. In Cartesian form, it is x square plus y square equal to k, a circle with center at origin and radius k units. Now substituting for x and y, we get a circle of the form u square plus v square equal to 2k square. Therefore, the image of the circle mod z equal to k is also a circle in W plane. Now let us consider the transformation W equal to Iz plus I. Let us show that the half plane x greater than 0 is mapped onto the half plane y greater than 1 in V greater than 1 in W plane. Consider W equal to Iz plus I. Now the real part u equal to minus y, v equal to x plus 1. Now let us find the image of the half plane x greater than 0. So x greater than 0 in z plane is mapped onto v greater than 1 in w plane. Now let us show that the region in z plane given by x greater than 0 and 0 less than y less than 2 is mapped into the region given by minus 1 less than u less than 1 and v greater than 0 in w plane under the transformation w equal to iz plus 1. It is a next problem. Consider the transformation w equal to iz plus 1. Now the real part u equal to 1 minus y, v equal to x. Now let us find the image of the plane x greater than 0 and y greater than 0 and y less than 2. When x greater than 0, we get v greater than 0. Similarly, when y greater than 0, u is less than 1. And y less than 2, the image is u greater than minus 1, which is shown in this figure. So, the image of x greater than 0 and 0 less than y less than 2, that is the rectangular region in z plane, is mapped onto a rectangular region bounded between minus u and minus 1 less than u less than 1 in w plane. Next example. Find the image of the square region with the vertex 0, 0, 2, 0, 2, 2 and 0, 2 under the transformation w equal to 1 plus I into z plus 2 plus I. Now using this transformation, we see that the coordinates 0, 0 are mapped onto the coordinates 2, 1 in W plane. Similarly, the image of the coordinates 2, 0 in Z plane is the coordinates 4, 3 in W plane. Similarly, 2, 2 of Z plane is mapped onto the points 2, 5 in W plane. And the image of 0, 2 of Z plane is 0, 3 in W plane, which is shown in this figure. So the square region bounded by the coordinates, given coordinates in Z plane, is again a square region in W plane bounded by the coordinates 0, 3, 2, 1, 4, 3 and 2, 5. Next example. Let us find the region into which the half plane y greater than 0 is mapped by the transformation w equal to 1 plus I into z. So let us find the image of y greater than 0 under this transformation. We get v greater than u. That is, the half plane y greater than 0 is mapped onto the line v greater than u in w plane, which is shown in this figure. Thank you.